Let's talk about gases. Oh, okay. What I meant was rules about gases.
Or sneeze or burp or fart.
Okay. What I meant was mathematical rules that describe the behaviors of gases that we're going to be that are going to be important in chemistry. How about that? Can we work with that? Okay, excellent. Okay, so we're going to have a set of mathematical equations that are called gas laws, and they're going to describe the behavior of gases in very quantitative ways. But we first want to look at some properties of gases that I suppose are consistent from one gas to the next that allow us to come up with mathematical expressions that describe the properties and the behaviors of gases. So let's take a quick look at some of those properties. Now, some of these properties are very easy to recognize and easy to understand, and we've seen them a lot of times because gases are part of our everyday life. Maybe like my helper in a few minutes ago. Gases are easy to compress. So we start out with a large amount of gas and we squash it into a smaller volume. And that's really important if you're talking about a barbecue tank or something like that. They expand quite rapidly. So you can have somebody making cookies in one room and you can smell it throughout the house. You can also have it that the gas will occupy, the amount of space that the molecule occupies is much, much larger than the amount of space that the molecule requires, but it's also much, much larger than the other states. And probably the best place you're going to see this is if you're boiling water, which doesn't sound that exciting, but if you take water and you see those bubbles coming up while the water is boiling, those bubbles are actually water vapor, where the water in liquid form has converted to gas form and has this big bubble. And if you've ever had water, things boiling over, a lot of that is just the water vapor in the gas state requiring so much more space. Rattles the pot lid, boils over, and can make a big mess. But anyway, those are our basic properties of gases. We'll probably list a few more as we talk about them in class, but those properties of gases, you'll notice there that we are talking about things like volumes, but also I suppose we're hinting at pressures, and those are going to be important when we talk about gas laws. So there are three main basic gas laws. We'll have a fourth one that combines them together, and then we'll have a fifth one a little bit later on. That's a separate video though. We're going to start with Boyles Law. Now, Boyles Law was first proposed by Robert Boyle. We don't really need to know his name, we don't really need to know his dates, but just understand that that's why it's called Boyles Law. Here's a picture of him. It's very old-fashioned looking. No, you don't have to draw that. Boyle described the behavior of gases with respect to the volume and pressure of a gas, the relationship between those two, when the thing was at a constant temperature. And what he found out, and we kind of know this, there's an inverse. So as the pressure increases, the volume decreases. So when you squeeze a gas, the gas ends up becoming smaller. And then the opposite is true as well. If you let the pressure go, the gas will expand and get larger. Mathematically, it would be represented by this formula. Well, this isn't really a formula yet. This is more of a proportional statement where you have the pressure on the bottom. As the pressure number gets larger, think about your fractions, your volume number is going to get smaller. We can turn that into a formula, mathematical formula like this, using a constant. The little k there is a constant. However, the form that we're going to use is this bottom one, where we're always going to be looking at a new volume or new pressure, or perhaps the first pressure, first volume, but knowing how something else has changed. So we'll have two pressures, two volumes, and as long as we get them paired up correctly, then we're off to the races. Next law, and we'll look at questions in a few moments, but the next law is Charles' law, and Charles was a Frenchman, Jacques Charles. Again, we don't really need to know his name, we don't really need to know his dates, we don't really need to know what he looks like, although he looks perhaps a little bit more modern, a little bit more fashionable than Robert Boyle. You could say that's because it's a little bit later in time, a little bit more recent, but it's also probably because he's a little bit more French. Robert Boyle was English, Jacques Charles was French, and whatever. He studied volume and temperature at a constant pressure. And we know from from experience that that's going to be more direct. As you heat up something, it typically expands. You heat up a gas, the gas is going to require more space. As one number goes up, the other number goes up. So as a proportional statement, it looks something like this. We can do the same thing, replace it with the proportional symbol, that little half fishy thing, with a constant, but the form that we're going to use is the bottom one, and it really doesn't matter if you have both, because one is just the total inverse of the other, or reciprocal, I suppose, but one, you can get the other. All we have to do is two things, I suppose, is number one, make sure that we pair them up correctly, so the first volume goes with the first temperature, but making sure that it's not, let's say, a standard ratio that we might be accustomed to from doing other work before. And then finally, Gay-Lussac, his law, although it may or may not be true that Gay-Lussac came up with this law on his own. Again, we don't need his dates. We don't know that don't need to know that it's debated whether or not he discovered or just sort of grabbed it and put his name on it. We don't need to know what he looks like. And at no point will you be asked to identify this picture with that person. But his is the pressure temperature law at constant volume. And we don't have as much experience with this, although if you have ever taken an aerosol can and looked at looked at the label and it says don't put this near a heat source, that's Gay-Lussac's law. If you take an aerosol can, which is full of gases, and if you put it near a heat source, you're increasing the temperature. Well, the volume of that can is constant until the lid pops off and things like that, and bad things can happen. But that one is also a direct relationship. As the temperature goes up, the pressure goes up. So we could start it like this, move to the constant, but what we're interested in, of course, is the final formula that we're going to use, which is one or the other. And again, much like Charles' law, we can take one and get the other. However, if you're kind of thinking about things, you might recognize that there's a bit of a mathematical problem, and then we can ask the question in a couple of different ways. If you look at the Charles law, or you look at Gay-Lussac's law, where we have a volume related to a temperature or a pressure related to a temperature, and you start thinking about the various options we have for temperatures, we could have a temperature of 0. We have that all the time in Canada. Right around, I don't know, December, where it starts getting cold, we'll have those days where it's 0 degrees. And throughout the winter, we also get into temperatures of negative degrees Celsius. What happens to our volumes and our pressures then? Can we have negative volumes or negative pressures? But the formula, as you see it, that's exactly what would happen. And if you think about watching, say, a weather report or listening to a weather report on an American channel, you might hear them talking about Fahrenheit, where the Fahrenheit scale and the Celsius scale are different. And we might be able to relate one to the other, but what would we do then? Well, the answer comes with something called the Kelvin temperature scale, which is going to give us something called an absolute 0. And if you look at the Celsius scale and the Kelvin scale, they're going to have a nice little relationship where, yeah, they're out by 273 degrees, which seems like an awkward number, but as you step up each degree, you're going up by the same amount of temperature. So 0 Kelvin, and we don't write the degree symbol here, 0 Kelvin, not okay, 0 Kelvin is absolute 0. There's nothing lower than that. That is the point at which everything stops. So if temperature is related to molecular motion, 0 Kelvin is the point at which all molecular motion has stopped. And it goes up from there. This is what's important for us. So you will not be given a temperature in Kelvin ever. You will always be given a temperature in Celsius. You'll have to convert it to Kelvin. And the conversion is really easy. Add 273. That's it. That's all you have to do. Done. Okay. Here are the the 3 gas laws that we need to know for after this video, and the Kelvin to Celsius, Celsius to Kelvin conversion. Those are the things that you really need to know, not the dates of when Boyle was and whether Charles is French or Spanish. It doesn't really matter. These things are important. Okay, there's also something that's kind of come up a little bit later. It's not so important for today, but since we've got a bit of a summary page going here, this thing here, SATP, stands for Standard ambient, which just sort of means room temperature, standard ambient temperature and pressure. And that's a set of conditions that have been defined by scientists. And we'll talk about those another time. You'll get to get used to them. Okay, I'm going to give you 3 typical questions. We're going to remind ourselves what formula we would want to use, and then I'm going to give you a chance to figure them out and compare answers. So here's one kind of question that you're likely going to see. You'll be given a situation of gases doing this at some temperature or at some volume, in this case some pressure, and then something changes. So we've got a volume, we've got a pressure, and then we've got another pressure, and you're asked to find the new volume. So if you look at the gas laws that we have, we're looking at this. We're looking at Boyles Law. Now we don't need to identify it as Boyles Law, we need to identify the formula that we're going to use. I'm not told anything about temperature, so I don't need to worry about it, which means it's probably constant. Another kind of question where we're using different kinds of things is this one, where we're given 2 temperatures and 1 volume. Okay, so now I'm looking at volume and temperature. Nothing about pressure, so ignore it. But don't forget, I need to convert the temperature into Kelvin. Now, little peek inside my mind in terms of me trying to find out if you know what you're doing. There's nothing about these temperatures that would give you any kind of red flag, right? Like if I gave you 0 degrees Celsius and you tried to use it, your calculator would tell you there's a problem. If I gave you a negative temperature and you tried to use it, your calculator would come up with a negative answer, and that would indicate there's a problem. If you were to accidentally use 15 degrees Celsius and 120 degrees Celsius, you would get what looks like a perfectly reasonable answer, and it would be wrong. So just be aware of that. You got to change the temperatures into Kelvin. And then lastly, for our sample questions is this one. You're given a thing here. Now you're not specifically told constant volume, but a metal container, those things that aren't real stretchy. So I'm kind of hinting at conditions. If I said a balloon, okay, those are stretchy. Metal cans, not so much. But you're given a temperature and a pressure, and then you're given another temperature. So you're going to be using Gay-Lussac's pressure temperature law, and of course changing the temperature in Kelvin. I would suggest you pause the video, try these questions on your own, and then come back and I'll show you the answers. Now hopefully you did that. I really hope you did that, because you're going to have to be able to do this on your own. Anyhow, you might as well get some early practice. The first question, where you're asked to come up with a new volume, I ended up with 1,800 milliliters, so 1,800 milliliters. By the way, if you put it into liters, that's okay. You'll have 1.8 liters. The second volume was 511.7. If you did it to a correct number of significant digits, you might have 512. And that's okay too. And then lastly, the new pressure. Same thing, I've carried more decimals and more significant digits than I really should have, but just so that our calculator is going to be saying the same thing. As far as gas laws go, the basic early gas laws, that's it. All we have to do is identify which law we're using, because you will only be told 2 things: a temperature pressure, a temperature volume, or a volume and a pressure. And then one of those things will be carefully left out. The other thing you have to do is identify the pairings, so that you make sure your first pressure and your first volume, for example, go together. And I guess the third thing is the turning the temperature into Kelvin. Turning volumes into liters isn't so important, although if volume 1 is in liters, volume 2 has to be in liters. If volume 1 is in milliliters, volume 2 has to be in milliliters. So as long as those units are the same, it doesn't really matter which ones are which. We'll try a whole pile of them in class. We'll use them in different ways. We'll expand the questions a little bit. And then very shortly we'll be talking about the combined gas law, where we put them all together and combine them. Talk to you in class.